Hello, good afternoon, sir.
Good afternoon.
I think you are switched on this fan. Fan is working, sir.
No. You are getting noise?
Some noise I am getting.
Okay. I don't even have the AC also switched off.
Okay.
Can I log out and join once again and see?
From system itself it is coming.
I think the fan is working for the PC. It's a laptop.
Oh.
But generally, I don't get this other time. I just log out and join once again.
Okay, sir. You better you do it.
Okay.
ಒಂದು ಫ್ಯಾನ್ ಸೌಂಡೇ ಅದು ಅಂತ ಇದೆ ಅದೇ ಲ್ಯಾಪ್ಟಾಪ್ ಇಂದ ಎಕ್ಸಾಮ್ ಅದೇ ಇರುತ್ತೆ ಇಲ್ಲ ಆಗಲ್ಲ
ಸರ್ ಜಾಯ್ನ್ ಆಗಿದ್ದೀರಾ?
ಹ್ಞೂ ಸರ್.
ಯಾಕೆ ಯಾರು ಬಂದೇ ಇಲ್ಲ ಇವತ್ತು?
ಮಧ್ಯಾಹ್ನ ಸರ್
ಜಾಯ್ನ್ ಆಗಿ ಮಲಗ್ಬೋದಲ್ಲ? ಲೈವ್ Hello.
Hello. Is it still there?
Still there, sir. Okay, sir. If you start presenting, I don't think that will be managed.
Okay.
Okay, sir. Good afternoon, sir. Audible, sir, from this side?
Yeah, I am. You are audible, yes.
Good afternoon to participants, and I request my colleague Dr. Nalina, Associate Professor in the Department of Chemistry, to welcome the participants and introduce the speaker of the today's session, Dr. Suresh D. Kulkarni. Please, madam.
Good afternoon, sir. Jai Shri Gurudev. Good afternoon, everyone. A warm welcome to all. Seeking the blessings of all Puja Swamijis. Myself, Dr. E. Nalina, Associate Professor, Department of Chemistry. It gives me an immense pleasure to introduce speaker for fourth session of 1 week FTP on advances in the synthesis of nanomaterials and their application in the field of science and engineering. That is Dr. Suresh D. Kulkarni, Associate Professor, Department of Atomic and Molecular Physics, Mahe, Manipal. Dr. Suresh D. Kulkarni obtained his PhD in chemistry from Karnataka University, Dharwad. Soon after his doctoral work, he joined Indian Institute of Science, Bangalore in 2008 as postdoctoral research associate. There he gained expertise on various projects in the area of nanomaterials. He joined Manipal Academy of Higher Education, Manipal, in 2012. His research work is focused on material chemistry, development of rapid synthesis methods for nanomaterials and thin films, wide band gap semiconductors for display applications, nanomaterials for environmental applications, band gap tailored materials for solar photocatalysis, and development of metal organic complexes as precursors to nanostructures. He has developed a low-cost rapid pyrolysis system for deposition of thin films. He has successfully completed three DST-funded research projects. He has active in national and international collaborations. Dr. Suresh D. Kulkarni has about 33 peer-reviewed international publications and about 35 papers presented in both national and international conferences. He has about 714 citations, H index of 15, and Heighten index of 23. He has successfully guided two PhD students and nine master's students. Presently, six students are doing their PhD under the guidance of Dr. Suresh D. Kulkarni sir. He is an active reviewer for several international journals related to nanomaterials and material chemistry. He has delivered several invited talks at a national forum, including 10th Bangalore India Nano Pre-Conference Lecturer Series 2018, Condensed Matter Physics and Application 2019, National Conference on Advances in Chemical Science 2018, DAE BRNS 12th National Symposium on Radiation and Photochemistry 2017, Third International Conference on Nanomaterials Synthesis, Characterization and Applications, Mahatma Gandhi University, Kottayam, Kerala, India. UGC sponsored national level seminar on photonics and its application 2016 and UGC sponsored national seminar on the world of nanoscience 2013. He is also a resource person for faculty development program organized by Ramaya Institute of Technology, Bangalore and KLE University, Belagavi. See, we are fortunate enough to have such a eminent person for today's session. Thank you, sir, for joining us. Sir will talk about fifth chemical approaches to the synthesis of functional oxide nanoparticles. Now, I request you, sir, to continue the session. Over to you, sir.
Thank you, madam, for your nice introduction and words of praise. First of all, I welcome all of you for this today's program. And what a nice time to have. We have a festival season where today day is generally meant for Saraswati, and we are here to gather more knowledge on the topic. And I congratulate Dr. Dinesh for having arranged this program for the all the participants, and I'm sure this series would have been definitely beneficial. And I'm going to add a few perspectives in the synthesis and the kind of things that are there in the field of nanoscience. I'll try to share, and I thank the organizers for giving this opportunity. And with that, I will try to start my session. I'll just share the screen. So, whether all of you are able to see the slide?
Sir, not yet visible, sir.
Sir, can somebody just confirm me you are able to look at the slides?
No, sir. No, sir. You go to share screen,
No.
sir.
Okay, now?
Yes, it's visible, sir.
Visible now? Okay. So, I'll go to the slideshow mode. Okay. So, I will not be able to look at the screen on the other side. So, if anything is there, please somebody can interrupt me and I can respond to it. Right now, I am looking only on my slides on the entire screen.
Okay.
Okay. Okay. So welcome to all of you, and today I'm going to discuss something about the swift chemical approaches to the synthesis of functional oxide nanoparticles. I'm going to discuss about a few of them, but with the intention what we are doing and what is the outcome. These are important things to focus, and we don't see many such approaches in this field. Okay. So I belong to Manipal Academy of Higher Education. I work in the department named Department of Atomic and Molecular Physics, Mahe Manipal. We are one of the prestigious research department in the university, and we have various funded research projects in the department running. And our institution, Mahe, is claimed institution of eminence by the MHRD in the recent past. So we try to do good quality research. That's the credit our organization has. And in the talk today, I'm going to discuss the importance of the synthesis, what the synthesis of nanoparticle has to do with, and the type of starting materials and the role of them. I'm going to focus mainly on the oxides, as my research area focuses on oxides, and mainly also I will try to focus on phosphorescent materials. And I will explain why there is a need for going for new method. And I'm going to touch upon two important fields where we have made good progress are the microwave synthesis and rapid annealing, and I'll try to say what other things can be done which will be beneficial for the audience. Okay, so generally in the research group that I have, we try to work on the rapid chemical routes for nanostructures and thin films. So we try to focus on a variety of applications. Okay. So we work on phosphors, we work on thin film depositions, we work on materials for photocatalysis, materials for upconversion nanoparticles, carbon composites, and magnetic materials, and all things have something in common, that is the chemical approach. Okay, here I have mentioned solution methods, but generally all are involving chemical approaches. And what we see on this slide, on the edges, you can see some of the SEM images of the nanostructures. All these are the nanostructures which are prepared in our laboratory by my PhD student, and some of them are done by myself when I was a postdoctoral research fellow. And generally, the theme of our work right now is focusing on these two important areas where we are working on environmental applications, including water splitting to generate hydrogen, water purification, and to develop some of the novel surfaces for environmental remediation. And the other field, we mainly right now focusing on display and solid state lighting, where we work on nanoparticles as phosphorescent materials for generating red, green, and blue component of the lighting industry. What you generally see in LEDs, the RGB becomes important part, and use of judicious combination of them can give us a perfect white light generation, which can go into the solid state lighting applications. And the central thing here remains the chemistry that we study, the materials chemistry, deals with the different type of defects that are induced in the material, and as a result, we get the different emission properties. Okay, I'll try to ponder upon some of the aspects in the due course of the time. Okay, so let me start with synthesis of nanoparticles. So when we generally speak about synthesis, is not a new term to chemists. Okay, and all of us, we know what is synthesis. So when we say a synthesis, generally we have some sort of precursors. Okay, we do try to do some chemistry. Either we end up with an intermediate or directly a product. But in case we have intermediates, sometimes you can have an intermediate which is a stable intermediate or an unstable intermediate, and the intermediate will be given some activation energy to drive that into a product of our interest. So this is what is generally about the general synthesis. So when we say so, the synthesis of nanoparticles, so the challenge becomes the nanoparticles. Okay, so when we say nanoparticles, all of you may be aware, the size that we are discussing is less than 100 nanometers. It's between 1 nanometer to 100 nanometer, though this boundary is not very hard and fast, but generally the field of nanoscience and technology deals with this regime which we call as the nano regime, 1 to 100 nanometers. And the starting materials are either molecules which may be ionic or they may be covalent molecules, covalently bonded molecules. And the molecules, as we know, the size of the molecules are in the angstrom size. Correct? They are of the order of angstroms, and therefore, when we want to prepare nanoparticles of our interest, we should see that the starting materials undergo a chemistry and they grow slightly bigger. Correct? And if this growth is not restricted, then it keeps on growing, and what we get is called as a bulk material. Okay, bulk material or bulk particles. When I say a bulk, it is generally the size beyond the nano regime. Okay, so there is one nano regime, we say colloidal range, and then we have bulk particles which may be 1 micron and above by and large. Therefore, when we want to synthesize nanoparticle, the important task remains is to control either the kinetics of growth or to stop the growth by using other chemistry that is possible. Okay. So in the process, what we have to do is there is a process called as nucleation. Nucleation is the first molecule when it is converted into the product. That is the first product molecule which is generated, that also may be in the size domain of angstroms, few angstroms, and therefore we have to allow the growth process and we should avoid agglomeration. Okay, so when the growth process is happening, if I use something, sorry, if I am able to use structure directing agents, so if I am able to use a structure directing agent, it can be some of the polymers, copolymers, or some of the surfactants. So if I are able to judiciously use them, I am going to control the growth and achieve nanoparticles. So this is possible, okay, only when you have to limit the growth and avoid the agglomeration. If you are able to avoid this agglomeration, you are able to control the particles to the nanoparticle regime. So this is the basic concept, which is quite general, and it becomes quite specific when you go to a particular material of interest. Okay, therefore one has to try and optimize and learn on the go how these things can be controlled. And if you are working with a similar family of materials, maybe the literature is able to help you, give you some clues what kind of general recipes can be followed. Okay, so when I say precursors, the starting materials, you can work with variety of starting materials. The most popular starting materials are metal salts because they are available for lower cost, and they are water soluble, and you can try to work along with that. There are other methods of synthesis. For example, you can see there are precipitation methods. You can precipitate a phosphor here, dysprosium doped calcium sulfate. So you can try and obtain the material. Okay, and this is one simple example. I will not go into the details, but what I am trying to say here is you can use simple salts, simple precipitation methods, simple drying process, and you have a technological material for some application. Okay, you can go up with a variety of other techniques. I'm sorry if it is not clear. I'll try to read it for you. What we are seeing here is co-precipitation. Co-precipitation. Precipitation, all of us we understand. I have to cross the solubility limit, correct? I can have a precipitating agent which will help me do so. I can precipitate different metal ions. In the example, you are seeing a Fe3 plus salt and a Fe2 plus salt. I can form Fe3O4 ferrite nanoparticles just by co-precipitation. I have aqueous solutions of these. I add a base like ammonium hydroxide. I can precipitate them together, separate the precipitate, okay, and try to heat it to convert that into oxide. That is about co-precipitation experiment. And you have another approach where you have reverse micro emulsion approach. We know about this micelles. We generally have surfactants. Surfactant has a polar and a non-polar side of a surfactant. The polar side is water soluble and the non-polar side is soluble in organic solvents. So when we have these, reverse micelles, if they are formed, reverse micelles act as a nano cages. They give small area where reaction can be controlled. Therefore, the particle size can be easily controlled in this approach called as a reverse microemulsion approach or a reverse micelle approach. Okay, and then we have the thermal decomposition. We can work with organometallic or metal organic complexes. When I say organometallic, all of us know there is a direct metal to carbon bond, and when we have metal organic complexes, we have a metal connected to oxygen, and the oxygen is connected to rest of the organic framework. So such materials can be taken to some higher temperatures and they become unstable, and your material of interest can be synthesized using a simple thermal decomposition. And this thermal decomposition can be assisted by a solvent, and what you are seeing in the picture is a solvent assisted thermal decomposition where we use some of the solvents which are high boiling. So some of the solvents can boil at about 300 degrees Celsius. Therefore, we can cause this kind of thermal decomposition at that elevated 300 degrees and form the material of our interest. You can control the size and shape of them by use of judicious surfactants. So these are the available techniques, but many of them are time consuming, and they have their own plus and minus. And one of the important thing I would like to say here is the precursors of this sort, which are called as the metal organic. What I am showing in the picture, you can see in the picture, I am showing a crystal of 1 beta diketonate aluminum complex. Okay, so it is aluminum acetyl acetonate complex, and such complexes are very much used in the technological industries which make thin films, which are generally used in our electronic devices, and for such processes these kind of precursors are used. But the similar precursors are also useful if you heat them, or they can sublime under low pressure. You can see they have a single step weight loss. They can easily form the vapors, and the vapor, if it is subjected to high temperature, it decomposes and forms the material. And using such materials without going into thin films and all, I will show you this kind of nanoparticles can be formed. And you can see some of the materials which are developed. You can see that they are formed as a core shell material. You have some material inside. If I can see here, you can see it is a kind of a fruit. I have one type of material inside, and I have one type of material on the outside of the material. And when we carefully analyze this, we see that I have carbon present. This material is rich in carbon, and this side of the material is rich in the oxide of our interest. So in this case, we formed aluminum oxide. So therefore, in the interior, I have aluminum oxide with small amount of carbon, and outside I have a carbon coating. And if I just heat it in the presence of oxygen, I am able to get rid of this shell, and I am able to get nanoparticles, spherical nanoparticles. You can see the shape, how symmetric they are in this picture. They are quite spherical, nice shaped, and this process takes only about 1 hour for me to prepare nice nanoparticles. All that you should have is, should have a judicious starting material. 1 hour of the process, you can form material. So one example I have shown here. Okay, so simple precursors which can be easily synthesized in every laboratory, including a undergraduate laboratory. You can synthesize them, you can purify them, use them to form beautiful nanoparticles. So that's possible, and you have to find out where they find applications. Accordingly, you can try to do the characterizations and see the properties of the material. Generally, when we speak about oxides, okay, a couple of things which are fundamental that everyone should know is the classification of materials based on their electronic band gap. So if I speak about conductors, all of us know there is a overlap of the valence band and the conduction band. And when we speak about semiconductors, you see that there is a finite energy gap between the valence band and the conduction band. And whereas if I say insulators, they have a large energy band gap. Okay, so semiconductors are important things in the technological industry. So you have this band gap, or you can have intermediate band gap to insulator and a semiconductor. So popular examples, if you take the zinc oxide and TiO2 are most widely researched nanoparticles. Both of them have a band gap around 3.3 electron volts, and which are called as wide band gap semiconductors. So they are not really semiconductors, but they are a kind of insulators, but having a band gap intermediate to that of semiconductors and insulators. So such materials are called as wide band gap semiconductors. They show semiconducting behavior, but they have a higher band gap. So metal oxides, these are important class of semiconductors. Why? They are important just because the important property they have is the chemical and thermal stability. These do not undergo decomposition even if they are heated to very high temperatures. They are chemically stable, they are thermally stable, and they can offer interesting properties including optical properties. Therefore, all of such material oxides, they find important applications in these fields: the solid state lighting, the lasers, the quantum dots, okay, the solar cells, and many others. What I have shown here are the phosphorescent materials, okay, which are important for the applications such as the television screens, okay, wherever you have displays, these things find important applications. So all the such materials come under the category of phosphors. Okay, let's understand how to synthesize these oxides. There are multiple synthesis methods to prepare oxides, including some of the things I discussed earlier. I discussed about co-precipitation. This I discussed, co-precipitation. There is a sol gel approach. Okay, you can prepare a sol. Sol, as you know, is rich in a solvent, and the solute of your interest is suspended, and by removing the solvent you can convert that into a gel. What you get is a zero gel, and that gel can be sintered, and you can oxide, prepare the oxides of your interest. But you can see I am listing two other methods which are considered as the physical methods. So synthesis of nanoparticles, generally when we teach, there are two categories. One is the chemical method of synthesis, and the other is the physical method of synthesis. Physical method of synthesis is simply starting with the material of your interest and mixing them and grinding them together. That forms the solid state approach. So in the solid state approach, what you do is you take bulk particles and you try to hammer them continuously and make the particle size smaller and smaller. When they reach nanoparticle size, you stop it. That's one of the solid state approach. Or you have when you have compound oxides to be prepared, you take bulk materials of your interest, you join them together in a particular ratio. For example, if you want to make zinc ferrite, let us say ZnFe2O4, you start with a zinc salt, okay, zinc oxide, and you start with the iron oxide Fe2O3, and you mix them together. You machine them, which is called as something called as a ball milling. You can see here. You can mix them together and sinter to high temperatures. In both these processes, you can see the processing times are of the order of several hours. So even in case of ball milling, some of the papers when you read, you can see that this is going for weeks. The process goes for some weeks. Okay, and the solid state approaches generally are taking high temperatures of the order of, let us say, 1500 degrees Celsius. Okay, and the process takes a lot of time, 12 hours, 14 hours, like that you are heating for high temperatures. So two things which we find objectionable, not really objectionable, but there is a scope for improvisation, is the processing time and the high temperature. Can we work on these? Is one of the important tasks. So what we did is we used a simple co-precipitation approach just to understand initially when we started working, okay, what is the time taken for synthesizing one phosphor, a chromium doped magnesium aluminate. Okay, so what we have done is we have synthesized the material, and you can see the material is heated to different temperatures from 500 to 1200 degrees Celsius, and you can see the XRD pattern. So this is a proper phase is formed only about a temperature around 700 degrees and above. You can see it is mostly amorphous here. The peaks are not well defined, all the peaks are not identified. But here, yes, we can say at 700 degree onwards the material is formed, and we understand that 700 is the minimum required temperature, and when we anneal to higher and higher temperature, you can see a good nice red emission can be obtained from our material. So this is a red phosphor. It gives emission in the NIR region around 700 degrees, and you can see the emission spectra here in this region, and a nice sharp red emission can be observed here. Okay, so what we understood from this is, okay, a temperature of 700 and above is required, and 1200 is giving you better results. That means higher temperatures of sintering temperatures are required. Okay, again same thing. Similarly, co-precipitation, we just changed the material. Now you use a aluminum here, chromium doped zinc aluminate, and we use a co-precipitation approach. You can see from 500 to 1200 we worked out, and we see that the properties of the material, a nice red emission here, okay, is coming only when you go to a higher temperature of 1200 degrees Celsius. So the details can be found out in our publications. But what to understand from this is there are two important observations. One is the solution methods are better. Why do I say solution methods are better? Is because the chromium, which is a dopant, can be homogeneously distributed in this zinc aluminate network. So we start our synthesis by salts. I start with a zinc salt, I start from an aluminum salt, I start from a chromium salt. All are dissolved in a beaker in the required ratio, and all of them are precipitated together. Therefore, the distribution of chromium within the host lattice is going to be extremely uniform. You don't get a similar homogeneous distribution in case of solid state or ball milling. The milling times have to be increased to improve the homogeneity. Whereas in co-precipitation, one single step, maybe about half an hour of stirring, you can introduce homogeneous distribution. You get the precipitate. All the circus we have to do is to separate the precipitate, that is the separation by centrifugation, then drying process and sintering process. Okay, and the synthesis, the starting material or the intermediate is obtained at relatively lower temperature, or rather I should say we obtain this precipitate at a room temperature. Then we have to introduce it to the furnace for higher temperature, but we have some advantages using solutions. Solution methods are better for the homogeneous distribution of the dopants. Okay, but since the time, annealing time is quite huge there, so time is valuable. So can we look for faster methods? Okay, so what we tried to look was the general synthesis strategy we adopted. We take a suitable precursor, then we use a solution synthesis. Later we didn't stick on necessarily solution synthesis, not necessarily solution synthesis at the later part, and then we adopted the annealing to transform the intermediates into the products of our choice. We did the structural and optical and other characterizations, optical studies, as we are interested in the phosphorescent materials. But the important thing we tried to look was annealing is taking a lot of time the way we do conventionally, that means using conventional furnaces. So what we have come up with is a new solution. We have developed in-house facility called as rapid annealing. I will give details of it in a short while. So instead of going for a routine annealing, we are now following a rapid annealing, and we are trying to compare how does it perform in comparison with a routine conventional annealing, and we try to go for the structural correlation between the structure and the properties that we observe for the material. Okay, and in this process we are looking for faster methods, and one of the important faster synthesis method we have adopted is a microwave assisted synthesis. Okay, all of us, we are aware of use of microwaves in cooking. Okay, most of our households have at least one microwave oven, and uh, this part of the work was funded by Science and Engineering Research Board, DST. I got a grant of about 40 lakhs in this, and this project is now completed, and following results are going to discuss some of the important highlights of this. So why microwaves can be used for synthesis? So for those who are not aware, we can see that the electromagnetic radiation in this region, okay, is considered, and it can have a wavelength of 1 millimeter to 1 meter. Okay, and the liquids can generally get heated under the influence of microwave, and there are two popular mechanisms through which it is understood that microwaves are causing the solvents to get heated. One of the mechanism is called as the ionic conduction. So you have charged particles which oscillate under the influence of microwave irradiation, and the oscillation leads to collision between neighboring molecules, and the collision produces the heat. That is one of the known mechanism. The other is the dipolar polarization. So dipoles, when you have polar molecules, you have dipoles, and the dipoles, they try to continuously realign with the direction of the electric field. And this difference in the frequency of microwave and the dipole, that leads to the molecular friction, and this molecular friction produces heat. The central concept in both these theories is there is the effect of microwaves cause molecular collisions. Okay, we know microwaves deal with the rotation of the bonds, and this rotation leads to friction, and the friction produces heat, and this heat is instantaneous. The important difference being, when you heat in a microwave, it is different than heating in a furnace or heating on a stove. What is the difference? The basic difference is, let us take, if we are heating water, we take a steel vessel and we place it on top of a stove or any other heating source, and we put water into it. So when we start heating, the first thing that happens is the vessel gets hotter, and the water which is in contact with the vessel gets hotter, and the interior of the water gets hotter later. Okay, so the heat, it has to actually go for a convection. It is called as a convective heating. The normal way of heating that we do in every day in our home are called as the convective heating, where the heating takes place when the molecule comes in contact with the surface that is getting heated, and slowly a convection is set, and you see the water boiling moves from top to bottom. So all of us are aware of it. But when we heat in a microwave, what happens is the entire volume of water gets heated instantaneously. At a given moment, all water molecules are hot. Okay, therefore what happens is the molecules or the kinetics is a sudden burst. Okay, nucleation takes place quite faster, and therefore you are able to cause a reaction much faster. We might have seen cooking using a microwave takes less time, whereas cooking using an ordinary stove takes little more time. If I want to boil water, I probably need about 20-25 seconds to start boiling water in a microwave oven, whereas I may take more than a minute or 2 minutes time on a conventional stove. So this is the basic difference between heating a solvent in a microwave radiation and putting it to use for synthesis. I'll just throw some light. Okay, this is the knowledge domain, how microwaves interact with solvents and how solvents get heated. Okay, more details can be found in one of the reference that I have given here. Those who are interested can please try to read this. And microwaves are used for synthesis, and the history dates back to about 1986. And this 1986, you can see microwave oven was used for the synthesis of organic materials, and now in most of the prestigious or commercial laboratories which produce commercial organic molecules, they use microwave synthesis as a faster and economical means of synthesis. Many of my friends who are in chemical industries, they are using these to prepare batches of organic compounds. And later, in about 1992, first time the microwaves were put to the use for synthesizing inorganic materials. And the first organic synthesis was done by this paper in tetrahedron letters. And Sridhar Komarnini et al. From the Pennsylvania State University, these are the people who were pioneers in putting microwave synthesis for inorganic material synthesis. Okay, and the advantages of microwaves is that the processing time is going to be low, the reaction times will be much faster, there will be selective heating. When we say selective heating, when we study how different solvents get heated, we can see that all solvents do not get heated equally under the influence of microwave. Therefore, based on the solubility, I can cause selective heating, and there is control over the size and shape. But if we are optimizing the chemistry, it is environmental friendly and the reactions are highly reproducible. These are the important thing for a chemist. The reaction has to be highly reproducible, and this the list of advantages makes everyone go at advantage to use microwaves for the synthesis. I will brief you some of the advantages of the synthesis that we have done. First of all, we synthesized zinc aluminate. Zinc aluminate is a material, wide band gap material with about more than 4.4 electron volt band gap. Generally, zinc aluminate material synthesis is reported not less than 1000 or 1100 degrees Celsius. And you can see that use of metal organic precursors. On the left hand side of the diagram, you can see the metal organic precursors are used, and just about 10 minutes of synthesis at a very lower temperature of about 180 degrees Celsius, you are able to get a precipitate. You can see in the bottom from the reaction while a white precipitate is obtained and when we do a X-ray pattern, we find that this corresponds to the zinc aluminate, and the material formed is single crystalline. All advantages are there for the material, and the synthesis takes place quite fast. Okay, so we have done various characterizations to understand the particle size of it. You can see all characterizations tell us that material is nanocrystalline. Okay, and the size is about 5 nanometer. The particle sizes here is about 5 nanometer, and each crystal is a single crystalline material. Each crystallite is single crystalline. These are the important outcomes, and all that is achieved. Crystalline material in 180 degree in just 10 minutes. That's a significant achievement, especially considering a ceramic like zinc aluminate. These are refractory oxides generally synthesized at high temperatures, but we are able to synthesize the material in quick time, and that too is at a lower temperature. And another important thing to see here, the material that we prepared has some kind of inversion. For those who don't know, I will tell what is inversion. If you look at zinc aluminate here, the zinc here is a 2 plus element. The oxidation state on zinc is 2 plus, aluminum is plus 3, correct? And these belong to a family of materials called spinel oxides with a general formula AB2O4. Here A, that is the 2 plus metal ion, will generally occupy a tetrahedral site, and aluminum is supposed to occupy an octahedral site. And since the synthesis is done in a very quick fashion, what we see is these metal ions do not get sufficient time to go to the place of their choice. Just 1 minute. Yeah. The metal ions, they do not find sufficient time to go to the site of their choice. So therefore, there is inversion. That means zinc occupies the place of aluminum, and aluminum ion takes the position of zinc ion. And what magnitude? About 33%. And what is the result? The result is that a material which is supposed to show only blue emission is now showing emission ranging from UV region to all the way up to 600 nanometers. And why is this so? This is because of the various types of electronic transitions that happen, various types of defects that are formed in the material. Okay, the word defect generally gives a kind of a negative feeling, but here I would like to say defects are useful. So these defects are producing light which is useful for expanding the light domain from blue to other green and red region. Okay, so this is an important insight for us which gave us the first idea of okay, we can employ microwaves and introduce different types of defects, and we can play around with the defects. There's also a possibility and control the emission properties. Okay, the details are there in our paper. Next, we try to dope chromium in the same material, and we can see that slightly in this case, because we have to use a chromium compound also, we have to change the synthesis conditions. Here the synthesis was accomplished at 220 degrees Celsius, and we had to optimize what is the minimum time required, and we identified that 60 minutes of time is sufficient. Okay, you can see a simple absorption spectra is telling me at 60 minutes all the chromium compound is turned into precipitate. Otherwise we had the green tinge of the chromium compound. And when we started doing the synthesis, you can see that at 40 minutes we have the material formed, but at 40 minutes the green color tells me all the chromium has not gone, and therefore we optimize the synthesis time to about 60 minutes, and within 60 minutes I am able to prepare 60 minutes and 220 degrees I am able to prepare this material which is crystalline in the as prepared form. Again, various characterizations to show that particles are quite small, dopant distribution is uniform, chromium is distributed everywhere uniformly, and look at the very nice emission pattern. Okay, these compounds are showing different types of emissions centered around 700 nanometer, the red emission, and very neat emission patterns are obtained by the material that are prepared. Of course, they require some amount of heat treatment for a short duration, but they give good lifetime. They can be used for biological applications. So these are some of the implications. So the point we see here in the last two slides, the common thing is we are using metal organic precursors, we are using microwaves, lower temperatures for synthesis. The material prepared is crystalline. Already I have formed the nanoparticles of my interest, and later we are tailoring the material properties. So what you see here are the tailoring the material properties by giving different temperatures. Okay, and you can see the emission properties are compared. What we prepared in some of the earlier slide I showed, we prepared the same material using co-precipitation. Now we compare with the microwave, and you can see the material can be prepared using microwave in a very quick time. Okay, similarly, we have put a cobalt as a dopant, and you can see again we can do all the same things. I will not spend much time on this. Again, here we are using metal organic precursors. Okay, material is crystalline, and the particle size is in the range of 5 to 10 nanometer. The particle is synthesized, and later we started synthesizing a well-known phosphor called zinc gallate with europium as a dopant. This is a commercial red phosphor. In your televisions, you have a red color which is coming on the televisions is because of the europium doped phosphors. And this time, instead of going for metal organic precursors, we started using metal salts as precursors. And with metal salts, you can see that the synthesis can be accomplished in a very quick time. Okay, and 5 nanometer spherical nanoparticles can be prepared of 5 nanometer size. Okay, they are crystalline, and the material property gives you predominant red emission in the 614 nanometer. So if you compare this with some of the literature, you can see that red emission, this is supposed to be the red emission, but all other emissions are dominant in the air case. These are unwanted emissions, especially from considering a television industry. And you can see here, our material shows predominantly 614 nanometer emission. And what we are showing here is by a hydrothermal approach synthesized by a literature I have mentioned below, whereas our sample prepared using microwave is giving good quality emission. And the quality of emission is shown by what you see in the picture. So it is giving you good quality red light, okay, and that is very close to the standards of the television industry. Similarly, we have prepared a chromium oxide using microwaves within 60 minutes, starting from a metal organic complex. Okay, nice particles are formed, single crystalline in nature. But the important thing here I would like to share is during the synthesis, when we did the 60 minutes of microwave synthesis, we get some intermediate product. And that intermediate product I am representing here. By XRD, I am not able to understand what is this material. But when we did a reflectance spectra, you can see it is showing more than 70% of reflection. Okay. So we started getting it out whether this is a useful material. So what we have done is, we have taken this material and taken steel plate, stainless steel plate. There is one stainless steel plate as such, and the other stainless steel plate was coated with this intermediate material that is formed. And we see that 1 hour we kept them under hot sun, and we see that after 1 hour, wherever we have this intermediate coated has about 5 degree lower temperature. That means this material can be put to use for this something called as rooftop coating applications. Wherever you have intense sunlight, the roof of the house gets heated, you can paint with this material so that the surface doesn't become hot. Okay. In the next part, I would like to throw some light on the rapid annealing as a new processing tool, and I'll tell you what it is and how it works. Okay, and in this process, there is a rapid thermal annealing which is closely related. I would like to differentiate between the terms. First, let us understand what is rapid thermal annealing. Rapid thermal annealing is used in industries, especially by the silicon industry, for tuning the properties of silicon wafers. And there are 3 ways of rapid thermal annealing. One is the rapid adiabatic heating using focused laser beams. But we can make out that laser beam spot sizes are quite small, and that becomes a drawback. And you can see the penetration depth. The heating is caused only to a little depth. And we have the rapid thermal flux based heating using arc lamps. So what are used as arc lamps, and what is happening there is non-uniform heating. You can see the heating is not uniform everywhere, and the penetration depth, there is a difference. The other one is there is a rapid isothermal annealing where halogen lamps are put to use, and in that case the heating is uniform. You can see the penetration depth is uniform to a quite long distance. So based on all this way of rapid thermal annealing is found to be beneficial and put to use, and the halogen lamp that are used has a typical emission of this profile. You can see that the major emission is around wavelength about 1000 nanometers, so it comes in the IR region. And with this knowledge, we have developed a system which is similar to rapid thermal annealing, but different than the rapid thermal annealing. So we call it as a rapid pyrolysis system. Later, I have used the term rapid annealing, and we developed this in collaboration with IISc Bangalore. And this project was also funded by, this was a separate project, and it was again funded by SCRB as a Young Scientist scheme. And I'm thankful to my collaborators in IISc for helping me in this. This rapid annealing system is a faster processing system where nanoparticles can be prepared, thin films can be prepared. And the schematic diagram of the system is shown here. And what we have here is actually the furnace is here, where majority of the heating process is happening, and we have all sorts of controllers to supply the starting materials. Okay, and the heating actually takes place here. Either the thin film deposition or the synthesis of nanoparticles happens here, and we have a system to maintain the exhaust. The important key aspects of this system is that we can attain high temperatures instantaneously, in quite quick time, like of the order of minutes. We can manipulate the material properties, especially the nanoparticles. We can manipulate their properties within minutes, and we have used to process several nanocrystalline ceramics. I'll show some interesting results which confirms these observations. Okay, so what we have done is we have earlier prepared chromium doped zinc aluminate using a co-precipitation method. The precipitate was put under the rapid annealing system, and you can see the heating and cooling cycle is like this. You can see that from a room temperature, within few minutes I can reach, say here I reach 900 degrees in about 4 to 5 minutes time. Okay, so at this time you can see 4 to 5 minutes time I can reach 900 degrees Celsius, and I can maintain the 900 degree for the time that I want, and then you see the material is rapidly getting cooled. So in altogether, start to end, within about 40 minutes of time, I have done the entire processing of synthesizing and annealing. Okay, so when I do an XRD pattern, you can see that within 40-50 minutes I have made nicely crystalline material. Okay, and the crystallite size is around 10 nanometer. Okay, and the particles image, you can see we have spherical nanoparticles, and the average size with this analysis is about 15 nanometer. And we did a comparison of the emission property. Okay, what we do for regular annealing with a furnace annealing on the top and a rapid annealing below. You can see the emission properties are comparable. We get good emission in a quick time of synthesis as well as processing. So the important thing to note here is with the use of rapid annealing, I have done two parts. One is the synthesis and as well as the annealing in a single go. So that is an important achievement of this system that we have developed. And later the question may come, okay, whether it works only for chromium containing materials. We have done on different materials, an undoped zinc aluminate here, there is no dopant. We have put a cobalt as a dopant, we have put iron as a dopant, and variety of other materials. And you can see these are the XRD patterns showing crystalline materials are formed within minutes. From start to end, in about 30 to 40 minutes, I synthesize as well as I finish the processing of these materials. It's important thing, so we published it in the Journal of Alloys and Compounds. Details can be found there. And all of you may be aware of combustion synthesis. Combustion synthesis is a synthesis technique where especially oxides can be easily synthesized in a beaker, in a laboratory, just by heating it on a hot plate. What we do is we start with the metal nitrates, and we mix a oxidizer to fuel ratio, we combine and we heat them. Suddenly during heating we say that there are fumes coming, and suddenly the liquid catches fire and the fire drives the reaction. That is why it is called as a combustion reaction. and after the reaction is over, you get your oxide. And this conventionally, if we do in our laboratory, takes about 1 to 1.5 hours to prepare zinc oxide nanoparticles, and within only 16 minutes, you can prepare nicely crystalline zinc oxide particles using a rapid annealing system. So that means rapid annealing can also drive combustion synthesis. Rapid annealing is useful, and the photoluminescent properties are also comparable with a regular annealing thing. So zinc oxide nanoparticles are prepared using conventional annealing. Okay, just for comparison of our materials, you can see the particle sizes are this. Emission is coming in this side. We have prepared materials which show white light. You can see different white lights. Our powder is put in a sample holder, and it is giving different types of emissions. Good white light is observed. These things fall in the white light region. The white light characteristics are done, which are comparable. Okay, and our material is showing good white light property. The important thing I would like you to notice, look at these captions on the corner. These are all the same material, just the way they are treated are different. They are heated once in air, once in nitrogen. The starting material is heated in nitrogen separately, oxygen separately. Just by changing the ambience of the material during heating, you can see that material can emit different lights. So this is an important aspect which is useful for the technological applications. We should know to maintain this ambience, and we are able to get cool white light out of this material. And in the previous slide, you saw the material was heated using conventional furnace annealing. And similarly, we have done zinc oxide nanoparticle synthesis using a rapid annealing system. Starting from a metal salt through a hydroxide, we have converted the hydroxide into an oxide. You can see that just at 300 degrees. When I say 300 degrees in the rapid annealing system, 300 degrees can be reached in just about 1.5 minutes, because the heating rates of the system are about 200 degrees per minute. So in 1.5 minutes, I can synthesize the zinc oxide nanoparticles, crystalline, okay, of this kind of shapes and material properties, giving this kind of broad emission, and these emissions correspond to different types of defects in the material, and they start giving you different colors. So I can tune the colors. You can see here that the emission color can be tuned from one end to the other end depending on a simple process. That too, it takes few minutes to do this, and the photoluminescence of this material can be employed in different applications. Similarly, europium has been doped. You can see a predominant red emission here of the europium sample, and red phosphor is formed. You can see that I can have this material synthesized in only 200 degrees Celsius. That means in 1 minute of time, the material can be synthesized. And this synthesis is quite fast. It's giving you, good optical properties, and these are beneficial because it reduces the processing time. Time is money in industry, and also the quality of the product is going to be much better. Even if I consider here, some of you may be noticing there is mention of 850 degrees Celsius. With a rapid annealing, 850 degrees Celsius can be achieved in about 4 to 5 minutes. Okay, so within 4 to 5 minutes, I have converted a starting material into a technologically useful material. Okay, so different aspects of this. So europium doped zinc oxide nanoparticles are prepared by furnace annealing also, just for comparison. And when we compare, we see that, okay, when we look at the time, rapid annealing is certainly a better option. And next the question comes, can we combine the microwave synthesized particles? Can they be handled using rapid annealing? So we experimented combining both the techniques, and what we see here is we prepared a magnetic material called zinc ferrite, and you can see nicely magnetic material with all sorts of magnetic characterization. You can see here ferrimagnetic materials are formed, and I can vary the size within minutes. In just 2 minutes of annealing, I can transform a material from 2 nanometer to 20 nanometer in size in just 2 minutes of processing using rapid annealing. This material, starting material, is made using a simple microwave oven and subjected to rapid annealing system for 2 minutes, and in 2 minutes I can have nice crystalline nanoparticles with good magnetic property. We can also form thin films. So we have used microwaves for the solution processing to deposit various novel metal coatings. In this, I am showing the coatings of silver on top of different surfaces. This is the bottom images show the zinc ferrite coatings. These are silver materials coated on glass here, on a aluminum sample here. This is on a piece of paper, and this is on a different type of glass. This is on nanoporous alumina. So what I am trying to show here is microwaves can, if once we understand the fundamentals of it, we can put them for use to prepare variety of coatings on different types of surfaces. We have also formed nano rods, okay, nano flowers of zinc oxide and other materials. We can control them. The control is in our hand by judicious combination of processing parameters and the chemicals that we employ. Okay, not only all these microwaves, using microwaves, a live working electronic device was coated with a magnetic material, and we see that the device is still performing and a better performing device, and this is a published work with our collaborators in Japan. And what we show here, this is what is going to be future technology. I don't know how many of you know, if you may be hearing about 5G. In the telephone industry, we are presently using 4G. You may be hearing about 5G. 5G and next level of technologies are heavily going to be dependent on what we are seeing on the slide. You need to see that the inductors which are present on the electronic oscillators, they need to be capped with magnetic materials so that you are able to avoid the electromagnetic interference, and therefore the device's performance will be higher. That means miniaturization of electronic gadget is going to be realized, and this is the first time in the literature we have shown that this kind of devices can be put in microwaves. It can be coated with a material of our interest, and we show that the material properties are improvised and still the electronic device is working. And that's published in one of our literature. You can go through it. And we can say that rapid annealing is a faster processing technique for nanoparticles. I'll show a couple of other examples also. In just about 15 minutes of this process of microwave synthesis, after microwave synthesis for 10 minutes in 200 degrees, okay, and few minutes of rapid annealing, what we have done is we have prepared the europium doped zinc gallate nanoparticles, put it for test, and what you can see here is we are able to tailor the material property to get very good red emission, and with a score of 87% color purity. It is very close to the television set standard. The television company standard is here. If you get here, it is considered 100%. Majority of the materials reach about 90%, and we score 87. That means our material is also having good compatibility to television industry. And use of rapid annealing on the same powder, what we have done is we are showing you that there is no change in the crystallite size. You see, from 7 nanometer to only 8 nanometer. Generally, whenever these particles are heated under high temperature, the particle size grows. Say 7 nanometer may go to about 30, 40 nanometers. But here, when we have annealed using rapid annealing, a much faster annealing, we have seen that there is no change in the size. Okay, but having said that, there is no change in the size, but there is a remarkable change in the optical properties of the material. You can see that the emission, the red color emission intensity is increasing with temperature here. Okay, and you can see that the material is showing a good score, 84% of color purity. Compared to the television set standard, the standard is here, and our metal property is showing 84% color purity. All this takes 10 minutes using microwave synthesis and few minutes using rapid annealing, about 15 minutes. So altogether within 1 hour, I start from starting material. Within 1 hour, I get a technological material in hand. That is something remarkable by combining the two techniques. The comparison of the optical property I am showing here. The conventional furnace annealing of the same material takes about 4 hours. Okay, and when I say 4 hours, actually I can take out the material only the next day because the furnace will be quite hot. Whereas in the rapid annealing process, you can take out the material in 10 minutes after the process. Within 10 minutes, you have the material in your hand with very good color output. Okay, the details can be found out in our publications. Couple of publications are there. Another example I am showing where I put terbium as a dopant. This gives you green emission, and this green emission is beneficial for television industry again as a green phosphor. And we have used rapid annealing to tailor the metal property here after a microwave synthesis. And you can see that gradually the material which was originally showing a bluish color turns a bright green emitting material. Now all that happens in only few minutes. Entire process takes about few minutes time, and we are able to transform in about 15 minutes. The material's emission moves from here to here. Okay, having said about the phosphor materials, I'll try to shift the discussion onto other materials. I told about the band gap can be tailored of the materials by judicious combination of metal ions. So microwave synthesis we have used to prepare materials which are useful photocatalysts. You can see that with the time the color of the dye is degraded. The materials are magnetic. You use a simple magnet. The photocatalyst can be separated. Just run the used pollutant, bring in the fresh pollutant, remove the magnet, and you are able to do this photocatalysis process again and again. So some of the publications have come out of this. I have listed them here. I'll show more on this in the next thing. Especially these reactions are visible light driven. Okay, I'll just go to the previous slide. The reactions that I have shown here, the kinetics that you see here, this is all happening under the room light. We have mercury vapor lamps, no, the lights that are used for street lights. We have used one such lamp, and with that we are able to drive chemical reactions. That means I can drive these reactions directly under sunlight. Okay, so these are the materials we re-optimized, and later we have prepared nice spherical particles, and these particles are coated with a material of our interest as a shell material, and you can see that the material becomes active under visible light. This is mesoporous, and it's able to show good photocatalytic activity just because of the particular band alignment that we have been able to optimize. The bottom line here is you take a dye solution, put small amount of our particles into it, keep them under sunlight, and after 1 hour you come back and see, you will see that the solution becomes colorless. And I have shown here in this thing that okay, up to 5 times of reuse of this material, the activity is not lost. That means there is no nothing like a photo corrosion. Majority of the materials suffer from this problem called as photo corrosion. The photocatalysts, when they are used first time, they behave well. Next time when you put to use, their activity comes down, and with the time, because of the photo corrosion, the surface gets damaged. and the material's performance goes bad. So in our case, we didn't observe anything like that. So even after multiple use under direct sunlight, our material is performing well. So that means the credit goes to the way it has been synthesized and the kind of defects that are playing a role in our material. So we are dealing with these kind of materials in a broader sense, and we are optimizing and moving forward to take them for multiple solar applications. That's the present ongoing work in our laboratory. So I'd like to tell, based on whatever conclusion the story I told so far, is that you can use micro solution synthesis to prepare nanoparticles, crystalline nanoparticles. You can use rapid annealing alone with a suitable choice of precursor and a process. You can prepare nanoparticles. You can combine both these and save enormous amount of time and energy and quickly achieve nanoparticles within minutes. So that's what I would like to say. With this, I would like to acknowledge the funding agencies, the Science and Engineering Research Board, the DST FIST program, which has funded a couple of instruments for us. Our institution, Manipal Academy of Higher Education, we have given 50% share for the DST FIST program. And I would like to thank Professor Shivshankar from IIC, Professor Nokant from IIC, who have been instrumental in guiding me during my postdoctoral days and helped me understand more technologies. And even now they have active collaboration, and I have active collaboration with them. They are continuously guiding and supporting my activities. Dr. Ranjit Sai, earlier he was in Japan and now he is in IIC Bangalore. Dr. Piyush Jaiswal, and my colleague K.S. Chaudhary, who have been helping hands in optimizing some of these techniques. My students, Samit Deepak, who have finished their PhDs now, earlier students, and majority of the work I presented belong to both of them. Some of the works I presented towards the end belong to Princeton and Anthony, who are presently pursuing PhD here. And these are other students who worked with me for their master's project and in the funded research project, and all have been a helping hand in accumulating these results, important outcomes of our work. And of course, my family for supporting my activities and bearing our long absences at home. Thank you. If any of you have questions, I would like to take them and answer.
Hello, sir. Hello, sir. Audible? Can you hear me, sir?
Yeah.
Hello. Okay, sir. Thank you, sir,
Yes,
for
sir.
your nice presentation. Thank you for your sharing your research experience and all. Hello.
Okay.
Sir.
Yes, sir. Please.
Dr. Janardhan Nayak from NMAMIT NITE Institute
Okay.
actually asking a question. Is it possible
Okay.
to synthesize? Is it possible to synthesize pure organic nanomaterials? If it is possible, how to characterize them?
If it is possible, how to characterize them?
Yeah.
Okay. So the question is right. It is possible to use microwaves to prepare nanoparticles. So the important challenge would be to control the crystallization process. So generally, when you prepare nanoparticles, you should see that one nanoparticle should not interact or should not undergo effective collision with the neighboring other organic molecule. So it is about the optimizing the synthesis conditions. Yes, you will be able to synthesize nanoparticles, and the way to characterize would be you have multiple characterization techniques. You can use a dynamic light scattering to identify, that is one of the technique. The other technique would be to use a scanning electron microscope. Okay, If you need to use a FECM and under low pressure because you are working with organic molecules, that would be possible.
Okay, sir. Thank you, sir. I think Dr. Janardhan Nayak convinced. So, if any more questions from the participants, sir, I will put into the WhatsApp. You can directly address them, sir.
Okay.
Okay, sir. Thank you very much, sir, for your 1.5 hour nice presentation.
Okay.
I asked my colleague Sayyid Nizamuddin to propose vote of thanks for this today's session. Please.
Thank you, sir. Good afternoon. So, myself, Syed Nizamuddin, Assistant Professor, Department of Chemistry. On behalf of AIT, Department of Chemistry, and all participants, and on my own behalf, I extend a hearty thanks to Dr. Suresh D. Kulkarni, an Associate Professor, Department of Atomic and Molecular Physics, MAHE, Manipal. So, thanking you for your sparing your precious time with us and sharing your knowledge and experience and your innovative ideas with us. Once again, thanks for your highly informative and valuable talk on swift chemical approaches to the synthesis of functional oxide nanoparticles. Thank you, sir. And also thank to our beloved principal for their guidance and help during this FDP program, sir. Thank you. Tomorrow's session by Dr. Narendra Reddy, Professor and Ramalingaswamy Fellow, Center of Incubation, Innovation, Research and Consultancy, Jyoti Institute of Technology, Bangalore, and is going to deliver a talk about on nano materials for textile and biomedical applications tomorrow by 10:30 to 12 o'clock. Thank you, sir. Thank you.